Today, we are going to look at the introduction to variation, where we will be talking about direct variation. Hello, my name is Samuel Kotoka, and coming right up is the introduction to variation. Alright, so we want to kick off this tutorial by looking at what the concept of variation is. So the concept of variation is used to show the relationship between two or more quantities. So when we talk about variation, we simply want to show the relationships between two or more variables or two or more quantities. So assuming we have quantity A and then we have another quantity, quantity B. We want to see the relationship between these two quantities and what effect does increasing quantity A has on quantity B and what effect does decreasing quantity A has on quantity B. Now, two or more quantities that are related to each other are said to either vary directly, inversely, or jointly. This means that there are three types of variation. The first one is the direct variation, which is the type of variation that we are looking at in this tutorial. The second is the indirect or inverse variation. Indirect or inverse variation. The last one is the joint variation. Like I said earlier on, for the purpose of this tutorial, we will be focusing on the direct variation. But in our subsequent tutorials, we will be looking at the indirect variation as well as the joint variation. And at the end of this entire series, we will be having a complete tutorial on variation with enough examples to prepare you for your exam or for your class. So let's look at what direct variation is and how we can represent direct variation mathematically. So direct variation. Now, two or more quantities are said to be directly proportional or vary directly when both quantities increase or decrease together. What we mean is, assuming we have quantity A and quantity B, if quantity A and quantity B are said to be directly variated, or the variation between quantity A and quantity B is a direct variation, an increase in quantity A causes an increase in quantity B. The same way, a decrease in quantity A causes a decrease in quantity B. This type of relationship or variation is what we refer to as the direct variation. Now let's look at how to represent direct variation mathematically so that you will be able to apply them in solving practical questions or practical examples in real life. So assuming we have the statement y is directly proportional or y varies directly as x raised to the power n. So we have y varies directly as x raised to the power n. If we have this statement and we need to express it mathematically, we write y, then we bring this sign, and then we write x raised to the power n. This is how we express direct variation mathematically. Now, y and x raised to the power n are what we are referring to as our quantities. Okay, so we are looking at the relationship between y and x, and we are saying they are directly related, and so we are using this statement to mean that they are directly variated, or the variation between them is a direct variation. So to remove this proportionality sign or the variation sign that we have over here, this alpha, okay, this sign is what we are using as our variation sign. So when we remove the variation sign, we need to introduce a constant. So the constant can be any variable at all so long as you define it and that variable is not one of the variables given in the question. So for this tutorial, I'm going to be using k as my constant of proportionality or my constant of variation. So my y now becomes y is equal to my constant multiplied by the second variable or the second quantity x raised to the power n. This is an expression to show direct variation between quantity y and quantity x raised to the power n, where k is my constant or my variation constant. Variation constant. So k is my proportionality constant, proportionality, proportionality constant or my variation constant. Now let's have a look at a statement or an example to see how we can practically apply this in solving a problem. So we have suppose m varies directly as n and m is 45 and n is 2.5. We are to determine the variation constant and write an equation for this relationship. We are also to use the equation we found to find the value of m when n is given as 4. So let's go ahead and solve this statement or this question. So we write down our solution. Now we can see that we have suppose m varies directly as n. So this is a statement showing what? Direct variation. So we write m is proportional or varies directly as n. Now to show the relationship, we remove the proportionality sign and we introduce a constant. So we have m is equal to kn, where we say the k is our what? Constant of proportionality or our variation constant. Now the initial condition that we are given is that when m is 45, n is what? 2.5. Okay, and we are to find m when n is what? 4. Now there are two approaches to solving a question like this. The first approach is this. So I'm going to use the first approach. After that, I'll use the second approach. So let me use approach 1. Let me use that as what? Method 1. So the first method is for you to find the constant of proportionality and then use that back in solving or finding the next quantity that you're supposed to find. So with that method, it goes like this. We have our statement is m is equal to kn. When m is 45, we have that to be equal to k, and then the value of n is 2.5. So to solve for our k, we divide by 2.5, 2.5, 2.5, and we get the value of our k to be equal to what? 18. So which means our constant of proportionality is equal to 18. Now that we have our constant of proportionality to be 18, we can go ahead, use this 18 to write a general equation for this relationship. That way, our equation now becomes m is equal to what? 18n. So these answer the first part of the equation that says write an equation for the relationship. So this is the equation for the relationship. Now, moving on, we want to find the value of m when n is equal to 4. So for that, we quote our statement or our equation now, which is what? Let me use this as II. M is equal to what? 18n. We have the value of n to be 4. So we substitute that over here. So when n is equal to 4, our m is now equal to 18 multiplied by 4. And if we compute this into our calculator, we are going to get the value of 72 as our m. Now this is the first method or the first approach to solving a question like this. Now, the second approach will jump the relationship between A or will jump the relationship between M and N by jumping the equation for the relationship. So we will not be able to get the equation for the relationship, but we will still be able to find the value of N. Sorry, the value of M. So let's look at that. In the second method, method 2, we use the equation we have over here. So we have M is equal to what? Kn. Okay, so we try to denote this by making it, let's say m1 k1 and then n1. Then we write another one, let's say m2 is equal to k2 n2. Okay, so we first of all try to make k1 and k2 the subject of each of these equations. Okay, we are using m1 k1 n1 and m2 k2 n2 because we have this to be, let's say this is our m1, this is our n1, this is our m2, this is our what, our n2. So we want to find the relationship between m1 and m2 and then n1 and n2, and in that way we can be able to find what, m2. So let's make k1 the subject. So making k1 the subject over here, we have m1 on what, n1. The same way, making k2 the subject over here, we have what, m2 on n2. But the constant of proportionality is the same for both cases, which means k1 is equal to what, k2. If this statement is true, it means we have m1 on n1 is now equal to what, m2 on n2. So this is the relationship between these two variables that we have, m1 and then n1, as well as what, m2 and then n2. So from here, we simply do the substitution of the values that we have over here and we find our m2. So let's go ahead and look at that. So our m1 is 45 on our m2, which is what, 2.5, and this is equal to our m2 on our n2, which is 4. So let me use this side. 18 is equal to m2 on 4, which implies that our m2 is now equal to what, 18 multiplied by 4, which means we cross multiply over here. So the 4 multiplies the 18, the m2 multiplies the, we are having our m2 to be equal to 18 multiplied by 4 would give us what, 72, as seen in the first method. Let's go ahead and see another example. Let's look at our first actual example. When an object such as a car is accelerating twice the distance d it travels varies directly with the square of the time elapsed. One car accelerating for 4 minutes travels 1,440 feet. We are to write an equation relating travel distance to the time elapsed and use the equation to determine the distance traveled by the car in 8 minutes. Now, as in the previous example, we see that for this particular example, it is the method 1 that can actually work for this example that we have over here, in the sense that the I aspect is asking us to find the equation relating the distance traveled to the time elapsed. So it is using the method 1 that we can be able to find the constant of proportionality and use that to find the equation relating the two variables. So let's look at that. So let's look at I. We have over here twice the distance traveled varies directly as the square of the time. We have 2d twice the distance varies directly as what, square of the time traveled. So this is the relationship that we have. To remove the proportionality sign, we introduce a constant, which means 2d is now equal to kt squared. Now for the first scenario, we have when time is 4 minutes, t is equal to 4. The distance traveled d is 1440 feet. So using these two variables, if we insert them into this equation, we will be able to find the value of k. So we have 2 multiplied by 1440, and that is equal to k. T is 4 squared. If we multiply 2 by 1440, we are going to get 2880 to be equal to the square of 4 is what? 16 multiplied by the constant k. So to find a constant k, we divide 2880 by 16, and that gives us the value of our constant to be equal to 180. Now that we have the value of our constant, we can now write the equation relating the distance traveled to the time elapsed as 2d is equal to kt squared, but we found out that k is 180. So our 2d is now equal to 180 t squared. This now becomes the equation relating the distance traveled to the time elapsed. Now, as you can see, this can further be simplified in the sense that if we divide through by 2, we get the distance to be equal to what? 90t squared, as the relationship between the distance traveled and then the time elapsed. So it's either you stop here as the relationship between the distance traveled and the time elapsed, or you can further simplify it down to get d is equal to 90t squared as the relationship between the distance and then the time elapsed. So with that out of the way, let's look at the II of the question. We are to use the equation to determine the distance traveled by the car in 8 minutes. This is very easy. So using the relationship we've established over here, we have d is equal to 90t squared. But we know that our time is what? 8 minutes. So we want to find the distance in 8 minutes. So which means we do the substitution. We have 90 multiplied by the time, which is 8 squared. So our distance is now 8 squared is 64. So we have 90 multiplied by 64. And this gives us the distance of what? 5,760 feet. So this is the distance traveled by the car accelerating at the same speed in 8 minutes. So let's have a look at another example. Example number 2. The electrical resistance in ohms of a wire varies directly as its length. If a wire of 110 centimeters long has a resistance of 7.5 ohms, what length has a total resistance of 12 ohms? Now, for the purpose of solving this tutorial or this particular example, I'm going to use the second method, which will show the relationship between the length of the wire and the resistance, and then using that to find the second length without necessarily finding the constant of proportionality. So let's write down our solution. So we have the electrical resistance. So we can see that over here we've not been given any variable to represent our electrical resistance and then the length of the wire. So it is advisable to define your quantities and denote them with a variable if one is not given in the question. So for us to do that, let's say let small r be our electrical resistance. In the same way, let small l be the length of the wire. Now that we have defined our quantities, let's go ahead and look at the relationship between them. So we have the electrical resistance varies directly as the length. So we have R varies directly as the length. To remove the proportionality sign, we introduce a constant and hence the equation becomes R is equal to KL. Now, we know that if the wire has the length of 110 centimeters, the resistance R is 7.5 ohms. Now, what length? So it means we don't know the new length in centimeters, which is having the resistance of what? 12 ohms. So we don't know that. So to find it, we want to say, let's make this equation becomes R1 is equal to K1 L1 as equation 1. And then we have R2 to be equal to K2 L2 as our equation 2. From here, let's try to make K1 and then K2 the subject. So if we make K1 the subject, it means we divide both sides by L1. So we now have R1 on L1 as our equation 1 from here. And then we now have K2 to be equal to what? R2 on L2 from our equation 2 over here. But the constant of proportionality for both is the same. So it means K1 is equal to what? K2. This implies that we can now have the ratio R1 on L1 to be equal to what? R2 on L2. From here, we can simply go ahead and find for L2. Okay, so this is L2, R2, this is R1, L1. So we have R1 to be 7.5 on L1, which is 110, to be equal to our R2 is 12 and then our L2 is unknown. Okay, so from here we simply do cross multiplication and then we find the value of our answer. So let's go ahead and do that. So we have 12 multiplied by 110 to be equal to 7.5 L2. Let me make some space over here. So 12 multiplied by 110 will give me 1320 to be equal to 7.5 L2. Making L2 the subject means we divide by 7.5. So we have 1320 divided by 7.5. So this will give us a length of 1320 divided by 7.5, and that gives us a length of what? 176 centimeters. So it means a length of what? 176 centimeters of the wire will have a total resistance of 12 ohms. Let's look at one final example. We have the stretch in the loaded spring varies directly as the load it supports. A load of 8 kilograms stretches a certain spring 9.6 centimeters. We are to find the constant of variation and the equation of the direct variation. We are to find what load will stretch the spring 6 centimeters. So let's go ahead and look at this, the solution to this problem. So we have the stretch in a loaded spring varies directly. So we say let S be the stretch in the loaded spring. And then let L be the load it supports. So we have L to be the load it supports. From here, we know that the stretch in the loaded spring varies directly as the load it supports. So which means our S is now equal to KL from our statement above. Now we've been told that the load of 8 kilogram, which means L is equal to what? 8 kilogram, causes a stretch in the spring of what? 9.6 centimeters. So we have our stretch to be what? 9.6 centimeters. So substituting these two values into the equation, we have 9.6 here to be equal to 8L. So our L is now 9.6 on 8, which now gives us an L value of what? Sorry, K. This is our constant. This is supposed to be K, our constant of proportionality. So our constant of proportionality from here becomes 1.2. Hence, from here, we can write the equation of the variation as S is equal to KL, but K is equal to 1.2, and hence our S is equal to 1.2L. So this now becomes the equation of the direct variation. From here, we can now go ahead and find what load will cause the stretch in the spring of what? 6 centimeters. So which means our load we do not know, but we know our stretch that we are expecting is 6 centimeters. So from here, we do the substitution and we have 6 to be equal to 1.2L. We simply divide through by 1.2 to get the value of our L. So our L now becomes 6 on 1.2, and this now gives us 5 kilogram, which means it requires a load of 5 kilogram to cause a stretch of 6 centimeters within the spring. Good learners, and welcome to today's video where we'll be talking about indirect or inverse variation. This is the online tutor, and coming right up is the introduction to indirect or inverse variation. As discussed in our previous variation tutorial, we said that variation shows the relationship between two or more quantities. In today's video, we want to look at the indirect or the inverse variation and how to write the inverse variation mathematically. We said that two or more quantities vary indirectly when one quantity increases and the other decreases. For instance, assuming we have quantity A, and then we have another quantity B. If these two quantities are inversely variated or vary inversely, if they vary inversely, what it means is that if quantity A increases, quantity B has to decrease. If quantity A decreases in size, then quantity B has to increase in size because of the variation being an inverse variation between them. So which means the relationship between quantity A and quantity B is an inverse relationship. So the progress of one means the what? The regression of another, and the same way the regression of another means the progress of another quantity. Let's have a look at an example. So if we have y varies indirectly as x raised to the power n, this relationship can be written in a mathematical form. So mathematically, we write y varies indirectly as x raised to the power n as y. This is our variation sign, and then to show an inverse relationship, we write 1 over the second quantity, which is what? X raised to the power n. So this statement is a statement to show that y varies inversely as x raised to the power n. Now, we need to remove the variation sign or the proportionality sign when we want to solve this particular equation. So to remove the proportionality sign or the variation sign, we introduce a constant. Now, like I said in the previous tutorial, when we remove the proportionality sign and we introduce a constant, the constant can be any variable at all, so long as it doesn't collide with the two quantities given in the question. So, for the purpose of our tutorial, I will be using k as my constant, but you can define your k as any other variable and use it in solving your question. So to further simplify this expression, we write y is equal to k. The k is now our variation constant or our proportionality constant. Then we write the expression 1 over what? X raised to the power n. Note that the k over here, which is the constant, is multiplying the equation 1 on x raised to the power n, which implies that we can rewrite this over here as y is equal to k on x raised to the power n. And this now becomes the expression to show that y varies indirectly as x raised to the power n, where y and x raised to the power n are our quantities, and then our k is our variation or proportionality constant. Let's have a look at a simple example to see how we apply this to solve a question. So assuming we have, let me say example 1. Assuming we have y varies inversely as x, and y is equal to 14 when x is equal to 3. We are to find x when y is equal to 30. So let's try and work out the solution for this problem. So, solution. We've been told in the question that y varies inversely as s. So let's write down that expression first before we proceed. So we have y varies inversely as what? X. So it becomes y, then the variation sign, then we have 1 over x, which is the next or the second quantity. To remove the variation sign, we introduce a constant. So this becomes y is equal to k multiplied by 1 over x. So this expression can be simplified as what? Y is equal to k on x. Now we've been told that when y is 14, x is 3. So with these two values given to us, when we do the substitution into this equation, assuming this is equation 1, we will be able to find our constant or our variation constant. So let's go ahead and do that. If we do the substitution, y is equal to 14 and s is equal to 3, we have 14 is equal to k on x, which is now 3. This implies that if we cross multiply over here to get the value of our k will now be equal to 14 multiplied by 3, which will give us a value of 42 when we compute this into our calculator. So 14 multiplied by 3 will give us what? 42. This means that the relationship between our y and x, which is the inverse relationship, ideally is supposed to be written mathematically as y is equal to 42 on s. So this becomes our variation equation. Now note that the variation equation here is the same as the variation equation here. The only difference is that here we've been able to compute the value of the constant when we were given two variables, that is y to be 14 and then x to be 3. Now let's now find the value of x when y is equal to 30. So when y is equal to 30, we have, let me create some space. So let's continue. Now, when y is equal to 30, we do not know our x, but we know that the equation or the variation equation is y is equal to 42 on x. This means let's do the substitution. Wherever we find y, let's substitute the value 30. So we have 30 is equal to 42 on x. To find the value of x, this has a denominator of y, so we cross multiply. So we have 30 multiplied by x will give us 30x to be equal to 1 multiplied by 42 will give us 42. So our value of x is now 42 on 30, which will give us the result of 42 on 30 will give us 1.4 as our answer. Now let's note something. Let me use a different color to denote that. We can see that in the first instance, when y was 14, x was 3. So which means y was big over here and then x was what? Small over here. Okay, we realize that when y in the second scenario has increased, okay, the y in the second scenario has increased from 14 to 30, we realize that the x value that we have has decreased from 3 to 1.4. So the x value has decreased. It has decreased from 3 to 1.4. This proves that the relationship between x and y is an inverse relationship, and the fact that as one value increases, the corresponding x value has to decrease because the relationship is an inverse relationship. Now let's have a look at an actual question to be able to solve for us to further enhance our understanding of inverse variation. So let's look at example number 1. The time required to travel a given distance, is inversely proportional to the speed of travel. If a trip can be made in 3.6 hours at a speed of 70 kilometers per hour, how long will it take to make the same trip at 90 kilometers per hour? This is a typical physics question involving what? The speed of a vehicle and then the distance traveled. So let's go ahead and look at the solution for this problem. So solution. We have here the time required to travel a given distance is inversely proportional to the speed of travel. So it means our first quantity over here is time, and then it is being compared to the second quantity, which is speed. Now, because we've not been given any variable to denote the time and then speed, we can choose our own variable to denote time and speed. So I will say let t be my time, and then let s be my speed. You can choose any variable that you want. So long as you define your variable, you are good to go. So we've been told that the time required to travel the distance varies inversely as the speed of travel. So it means our time t varies inversely as the speed of the vehicle. So to remove the proportionality sign, like I said, we introduce a constant. In our case, our constant is what? K, now multiplied by 1 over s. So it is safe to write that t, which is time, is equal to k on s. As at this point in time, I believe we all know how come we have this. So let's proceed. We've been told that if a trip can be made in 3.6 hours, let me use another color for that. So if a trip can be made in 3.6 hours at the speed of what? 70 kilometers per hour, how long will it take to make the same trip at what? 90 kilometers per hour. So let's look at that. In the first instance, we have the time to be 3.6 hours, and then we have our speed to be 70 kilometers per hour. So let's go ahead and calculate the value of our constant of proportionality. So to do that, we substitute the value of the time and then the speed into the equation we have over here, assuming this is equation 1. So we have 3.6 to be equal to our constant on the value 70, which is our speed. So to get our constant, we simply cross multiply. Our constant now becomes 3.6 multiplied by 70. So if we compute 3.6 by 70, we get 252 as our result, or the value for k. This means that the actual equation showing the relationship between the time traveled and then the speed is equal to time equals 252 on the speed. So this becomes our actual variation equation, assuming the question asks you to find the variation equation. So this becomes our variation equation. Now, the second aspect of the question is telling us to find how long it will take to make the same trip but at a different speed. So we have what? A higher speed. Okay, so our new speed is 90 kilometers per hour, and we are to find the time it will take for this. Now, straight ahead, there is a conclusion that I can make from this question. I know that my initial speed was 70 and it has increased to 90. And the fact that the relationship between the time and then the speed is an inverse relationship, I am confident enough to say that I'm expecting a time which is less than 3.6 hours as my time travels in this case. So let's go ahead and see if that is actually true. We know that our variation equation tells us the time is now equal to 252 on s. So it implies our time is equal to 252 on our speed over here is 90 kilometers. So we have 90 kilometers per hour. If we compute this into our calculator, 252 on 90 will give us 2.8. Then we add hours to it. So it means for the same trip, if the speed of the car or the vehicle is increased to 90 kilometers per hour, it will take a lesser time, which is 2.8 hours, for us to reach the same destination. So this now proves that what the statement I made earlier on, that I'm expecting my time to be lesser than the initial time given, is actually true. And the fact that the speed has increased from 70 to 90 means the time has to reduce, and that is what we've seen over here, that the time has reduced from 3.6 hours to 2.8 hours. Now let's have a look at something. For those of us who are physics students, there is an expression that is really important for us when we are doing dimensional analysis. Okay, so we are going to go through that. But if you're not a physics student, don't worry, this expression is also going to be helpful to you as well, so long as you are doing variation. So we have the frequency of a string. So the frequency, which I'm going to denote by F, of a string is inversely proportional to the square root of its mass per unit length. Okay, so the frequency is inversely proportional to the square root of the mass per unit length of a spring. Mathematically, if I say let my frequency be F, okay, let frequency be F, and then let my mass per unit length, okay, so mass per unit length be equal to m, it means this expression I have over here can be written as frequency varies inversely as the square root of the mass per unit length, which is m. So assuming we have two different strings, okay, so for two different strings, we are saying string A will have the frequency fa to be what? Proportional to 1 over the square root of the mass per unit length of A, or alpha. Okay, and then for the second string, we have frequency of B to be proportional to 1 over the square root of the mass per unit length of B. So from here, I can further simplify this to be, let me simplify this first. My f of A will now be equal to k, which is the constant, on the root of what? The mass per unit length of A. And the f of B, the frequency of B, will be equal to k, which is our variation constant, on the root of what? Mass per unit length of B. But since k is a proportionality constant, okay, since the k we have over here is a proportionality constant, it doesn't matter whether it's for spring A or spring B, our proportionality constant, which is what? K, or our variation constant, variation stroke proportionality constant, is the same, which implies that if this is Ka and Kb, then we are saying that Ka is equal to what? Kb. This implies that if we make Ka the subject over here, we are going to have the expression Ka to be equal to f of A multiplied by the square root of Ma. The same way we have Kb to be equal to f of B multiplied by the square root of m of B. This way, if these two are actually equal, it means that from this expression, you can have f of A multiplied by the root of Ma will be equal to f of B multiplied by the root of what? M of B. If you want to express these two guys in a ratio form, okay, where we have f of A and then f of B at one side, we divide, if we divide this side by what? F of A, we need to divide this side by what? M of B. In that way, we are going to have, if we maintain the f of A over here, we are going to have f of A on f of B will now be equal to what? The square root of what? M of B on the square root of what? M of A. So this becomes the expression to show the relationship between two strings having frequency and their mass per unit length. So let's note this expression as we are going to use it in solving a problem for the next question. So let's look at the next question that we have. So example number 2. Two strings of the same length and under the same tension gives nodes or frequencies in the ratio 4:1. Find the corresponding ratio of the masses of the strings. We get to realize that over here we've not been given any values for the frequency and the mass per unit length, but we've been given a ratio. In this way, it is hard to compute two frequencies to get a proportionality constant. So in this example, we need to use the expression that we've been able to derive in the previous scenario that I showed for us to be able to solve this question. So we are going to use the expression we have over here, this expression, to solve the problem in the next question. So let's go ahead and look at that. So we've been told that frequency A, the ratio of frequency A to frequency B is what? 4:1. Okay, if that is the case, we've been able to establish in the first case that frequency A to the ratio of frequency A to frequency B will be equal to the square root of the mass per unit length of frequency B, and then string B, to the mass per unit length of string A. This was the expression that we derived. Okay, so straight ahead we can go and solve this problem. So we have 4/1 as the ratio we've been given over here, that is the ratio of f of A to f of B, to be equal to the square root of MB over what? MA, the square root of MA. So to solve this, we need to get rid of the square root sign we have over here. So we square both sides. If we do that, we get rid of the root signs over here, and then we have m of B on m of A to be equal to 4 squared will give us 16, and then 1 squared will give us 1. Okay, so which means the ratio of, if we interchange the position over here to have our A at the top, MA on what? MB will be equal to, we need to interchange this side as well, will be what? 1:16. This implies that the ratio of what? MA to what? MB will be equal to what? 1:16. This implies that the corresponding ratio of the masses of the string, that is the mass of string A and then the mass of string B, the ratio is what? 1:16. Hello OT learners, and welcome to the continuation of our variation series, where we'll be talking about joint variation. This is the online tutor, and coming right up is the joint variation tutorial. Right, so previously we talked about direct and indirect variation, but today we want to talk about what a joint variation is. Now, I recommend you to go and watch our previous tutorials on direct variation and inverse or indirect variation. In that way, you are familiar with the topic of variation and you can easily proceed to study joint variation. So let's go ahead and have a definition of what a joint variation is. So we have a joint variation when there are two or more quantities related to each other. This can be a combination of direct and indirect variation. So a joint variation is simply just the variation that exists between multiple quantities. We realize that in the first two scenarios where we talk about direct and indirect variation, we realize that the relationship were only between what? Two quantities. Two quantities. Okay? And these type of variations, we say they are either direct or indirect. Now, in a situation where you have, let's say, two or more, for instance, maybe three, four, or five quantities, this type of variation now becomes what? A joint variation. Now, a joint variation can include two direct variation or two indirect variation, or it can be a combination of what? A direct variation or an inverse variation all together coming to form what? A joint variation. So we said a joint variation, we have a joint variation existing between what? Two or more quantities that are related to each other. So let's have a look at some few cases and see how we can express the variation when we've been given a statement involving joint variation. So let's look at case 1, what I will call as case 1. So I have A varies jointly as B and the root of Z. So let's look at that. We have A varies jointly as B, A varies jointly as B and the root of Z. Okay, now this expression can be written in a mathematical form. Okay, so mathematically we can see that we have three quantities. We have quantity A, okay, then we have quantity B, and then we have quantity what? Z. Okay, so the relationship exists between these three quantities. Now we see that A varies jointly as B, okay, means it's a direct variation between A and B. So it's going to be A varies directly as B. And the same way we have A varies jointly as B and the root of Z. So it means A also varies directly as what? As the root of Z. So the square root of Z. Okay, now because this is a joint variation, we combine these two variations to form one variation. Okay, that becomes our joint variation. So we have what? A direct variation over here, we have another direct variation over here. So we combine all together, it becomes a joint variation involving what? Three quantities. So this becomes A varies directly as what? B and the root of Z. So we multiply the two other quantities that A is being what? Jointly variated to. So with this expression, we can easily go ahead and remove our proportionality sign over here, and we introduce our constant. In this case, it becomes A is equal to K multiplied by B multiplied by the root of Z, where A, B, and Z are our quantities. Okay, they are our quantities, and the K, okay, over here becomes what? Our variation or proportionality constant, or proportionality constant. Now let's have a look at another case which I call the case 2, and see how we can express that. So I'm going to use the statement s varies jointly as the square of y. So s varies jointly as the square of y and inversely as the cubic root of z. We have to write this expression mathematically. So let me create a column and use another color for that. So over here we can see that we have one variable which is our x, then we have another variable which is our y, and then another variable which is our z. So the variation exists between these three variables or quantities. So for x, we have x varies jointly as the square of z. This is a direct variation between x and y. So we write that as x varies as the square of y. So this is our first variation, and it is what? A direct variation. Now we have over here and inversely as the cubic root of z, which means s also varies inversely, which becomes 1 over what? The cubic root of what? Of z. And this is what? This is an inverse or an indirect variation. Okay, so if we combine these two, we get what we call the joint variation between what? X, y, and z. So let's do that. To combine it, we simply multiply this and this, okay, whilst maintaining the x and the variation sign. So we have s varies as y squared on the cubic root of z. So we can now remove our variation sign and introduce our constant. So it means s is equal to k multiplied by y squared on the cubic root of what? Of z. So with this basic introduction, let's go ahead and have a look at some few examples to see how we can use the joint variation in solving practical problems. So let's have a look at example number 1. We have z varies jointly as s and the square of y and inversely as w. If z is equal to 25 when s is equal to 10, y is equal to 2, and w is equal to 8, we are to determine an equation and find the value of z when s is equal to 12, y is equal to 2.5, and w is equal to 10. So this is very easy. Let's go ahead and find a solution for this problem. So we write down our solution. So we have z varies jointly as x. So we have z varies jointly as x as one variation, and the square of y. So we have z also varies as what? The square of y, and inversely as w. So it means z again varies inversely, this time as w. So we have a direct variation, another direct variation, and then we have one inverse variation. So if we combine all of this, we are getting what? Our joint variation. Now note, if you are writing this for an exam, please do not write the direct variation and the inverse variation that I have over here. This is just for explanation purposes. you can write these direct variations and combine all of them to form the joint variation. That could fetch you an extra mark, but please do not write this over here. So it means in all, we are saying that z varies directly as x and directly as y squared and inversely as what? W. Okay, so this is how we write it together. So this is, first is the direct variation, so you multiply it with the next direct variation, and then we divide it by the inverse variation, so that gives you the joint variation. So this becomes our joint variation. Okay, so from here we can remove the proportionality sign and introduce our constant. So it means z is equal to x is equal to k x multiplied by y squared on w. So this becomes our what? Our equation in this case. So let's go ahead and find the value of k, substitute it back into this equation, which we are saying is equation 1, and then we can be able to what? Use that as our equation for this example. So let me use a new color or a different color. So we have, when z is 25, s is equal to 10, y is equal to 2, and w equals 8. So we simply have to do what? Substitution of these values into equation 1 to get our constant. Simple mathematics. So we have our z to be equal to k x y squared on w. This implies that our z, which is 25 now, so we have 25, is equal to our k, we do not know, our x is 10, our y is 2 squared, and our w is 8. If we further simplify this, we are going to have 25 multiplied by 8 over here, and that is going to give us a value of what? 200 to be equal to 2 squared is 4 multiplied by 10 will give us 40 multiplied by the constant 40k. So we divide both sides by 40 to get the value of our constant. So our k, which is our constant, becomes this, cross out this, 4 goes into 25 times. So it means our variation constant or our proportionality constant is equal to 5. So hence I can go ahead and write my equation for this problem to be what? Z is equal to 5x multiplied by y squared all on what? W, as my variation equation, or the equation that I was told or asked to find over here. Now let's continue with the latter end of the question. We are to find z when x is 12, y is 2.5, and w is 10. This is easy. So our z is equal to 5 multiplied by the value of x is 12, then again multiplied by the value of y is 2.5. We square that, then we divide it by the value of w, which is equal to 10. So if we compute this, we get to realize that the top will give us a value of what? 375 on 10. So this is equal to 37.5. This means our value of z when x is 12, y is 2.5, and w is 10 is equal to 37.5. So let's go ahead and have a look at another example. So example number 2. The surface area of a cylinder varies jointly as the radius and the sum of the radius and the height. A cylinder with height 8 cm and radius 4 cm has a surface area of 96 pi centimeters squared. We are to find the value or we have to find the surface area of the cylinder with a radius 3 centimeters and a height of 10 centimeters. So let's look at this problem. So we write down our solution. So we have a surface area of a cylinder. So let's say A is our surface area. Okay, so let A be our surface area. So the surface area of a cylinder varies jointly as the radius. Okay, the end is the break, okay, between the variables. So we have, firstly, the surface area varies jointly as the radius. Okay, so this means our surface area varies as the radius. And okay, the end over here breaks between the radius and the second quantity, and the sum of the radius and the height. So it means the area also varies as the sum of the radius and the height of the cylinder. Okay, so it means we have two direct variations. So if we combine it, we are going to get our joint variation. So this means we have our area is proportional to the radius multiplied by the second variation, which is what? R plus H, as our variation for the joint equation. So to remove our variation sign, we introduce a constant. We have A is equal to K, which is our constant of proportionality or constant of variation, multiplied by R, multiplied by what? R plus H. So let's continue with the second aspect of the question. We have a cylinder with height, so we have height to be 8 centimeters and radius to be what? 4 centimeters. And in that case, the area is what? 96 pi centimeters squared. So let's go ahead, use all these values and find our variation constant before we proceed to the latter end of the question. So if we do the substitution, we get to realize that we have 96 to be equal to the value of K multiplied by 4 into bracket 4 plus 8. This means we have 96 to be equal to 4K into bracket 4 plus 8 will give me 12. And then that 12 multiplied by 4 will give me 48. So from here I have 96 is equal to 48K. If I divide through by 48 to get the value of my constant, it means my K will be equal to, this is supposed to be 96 pi, so remember to add your pi. This is 96 pi. Okay, so if I divide through by 48, I get to realize that 96 pi divided by 48 will give me what? 2 pi. This means that my variation constant is equal to 2 pi. This therefore means that the actual area of a cylinder, okay, the area of a cylinder is given to me as what? The constant, which is what? 2 pi multiplied by what? R into bracket R plus H. So this now becomes my area of a cylinder. Please, for verification's sake, you can search Google for the area of a cylinder and see if the expression we've obtained over here is actually the formula for the area of a cylinder. So let's proceed. We have to find the surface area, so it means the second aspect, we don't know the surface area of the cylinder when we are given the radius to be 3 centimeters and then the height to be 10 centimeters. So we have to find the area. So area we don't know when the radius, when the radius is 3 centimeters and then the height is what? 10 centimeters. So let's go ahead and look at that. So it means our area will be equal to 2 pi multiplied by the radius, which is 3, and then multiplied by the sum of what? 3 and the value 10. So this is going to be 2 pi into brackets 3 multiplied by 13. If I multiply 2 by 3 by 13, this is going to give me the value of the area to be equal to what? 78 pi, and then I add the unit, which becomes centimeters squared. So therefore, it means that the area of the cylinder, when the radius is 3 centimeters and then the height is 10 centimeters, is equal to 78 pi centimeters squared. Let's have a look at one final example. We have, if z or z varies jointly as x and the square root of y, and z is equal to 6 when y is equal to 3 and y is equal to 16, we are to find z when x is equal to 7 and y is equal to 4. Example number 3. If z varies jointly as x and the square root of y, and z is equal to 6 when x is equal to 3 and y is equal to 16, we are to find the value of z when x is 7 and y is equal to 4. So let's go ahead and write down our solution. So we have our z varies jointly as x, so this is our first break, and the square of what? Y. This is the end of our second variation. So we have z varies jointly as x, which is a direct variation, and then z also varies as the square root of y. So we have square root of y. So we combine these two variations and we get z varies as x and the square root of y jointly. To remove our variation sign, we introduce a constant k, which now multiply x and then the square root of y. We have here, when z is 6, s is 3 and y is 16. So we have z to be equal to 6 when s is 3 and then y is 16. So let's do the substitution to find the value of our constant. So when z is 6, we have is equal to our k multiplied by x, which is 3, multiplied by the root of what? 16. We have 6 is equal to root of 16 is 4, multiplied by 3 will give me 12. So I have 12k. So I divide both sides by 12 to have my value of the constant. So my k is now equal to 1 over 2, because 6 goes into itself 1, goes into 12 2. So my variation constant or my proportionality constant in this example is 0.5 or half. So which means my equation for this joint variation becomes z is equal to 1 over 2 x multiplied by the root of y. Now we are to find z, so we do not know z in the second scenario when x is 7 and y is equal to 4. So let's do the substitution. So we have z is equal to half multiplied by the value of our x is 7 and then the value of our y under the root is equal to 4. The root of 4 will give me 2. 2 multiplied by 7 will give me 14, and half of that is still 7. So let's do this. So it means my z is equal to half multiplied by 7 multiplied by the root of 4 is equal to 2. So it means my z is equal to, the 2 here will cancel here, give me 1. So 1 multiplied by 7 multiplied by 1 will still give me the value 7. So it means when my x is 7 and my y is equal to 4, my z or the value of z is also equal to 7. So thank you so much for watching this joint variation tutorial. This brings us to the end of our short variation series, where we firstly look at what direct variation is. We also proceeded to look at what an inverse or an indirect variation is, and in this tutorial we learned about what joint variation is. So I'll be compiling these three tutorials to make a full video tutorial on variation, and I will be posting it in our variation playlist for you guys to watch. So thank you so much for watching. My name is Samuel Kutuka, the online tutor, and you can follow me on the social media platforms listed below. So you can follow me on Instagram at the online tutor 990, or you subscribe to my YouTube channel where I share educational content all around everything, including mathematics, science, physics, biology, history, PowerPoint, Excel, Word, and motivational tips and study tips that will help you pass your exams and then be the best version of yourself in this life. So thank you so much for watching, and I'll see you in the next video. Bye bye.